Good afternoon, everybody. My name is Matthias Deeg, and in the next couple of minutes, I want to talk about a tiny research project I did together with my colleague Philipp Buchecker almost a year ago, and it's about bypassing a biometric face authentication system. So, as already mentioned, my name is Matthias. I'm interested in information technology since I was a kid back in the 1980s. I studied computer science at the University of Ulm a long time ago, and I've been working as an IT security consultant for a company named SYS since 2007, and I'm also responsible for research and development there. So the agenda of my talk is as follows. At first, I want to introduce some of the technology we'll be seeing on the slides. Then I want to shortly mention previous work of other researchers concerning biometric authentication systems from the last decade I'm aware of, and the knowledge I used actually. Then I want to present the attack surface and the attack scenario, the found security vulnerability I am talking about, and I also try to demonstrate it live here, a live demo. And at the end, there will be some conclusion and recommendations concerning face authentication and one specific face authentication system from Microsoft, the Windows Hello one. And when there's still time, there's some Q&A. Okay, so when talking about biometric face authentication systems, we are also talking about face recognition technology. And what you need for this is, of course, a kind of sensor. In this case, the sensor is a camera. So the biometric sensor is a camera. This sensor acquires data, which is later on processed. During the processing, there is feature extraction, where you are trying to find specific landmarks, or so-called landmarks or alignment points in an image of a face. For example, the geometry of the face, between different parts, between the nose and the mouth, or distance between the eyes, stuff like that. And then there will be a mathematical representation of your face, simply a model. Then there are important performance metrics when designing and also implementing a biometric system. These most important metrics are the so-called false accept rate, FAR, the false reject rate, FRR, the equal, or also called cross-error rate. Then there are terms like accuracy and confidence, which are defined differently from manufacturer to manufacturer. And later on, we will see how, for instance, Microsoft defines the accuracy of its Windows Hello face authentication system. What's also important is a process called enrollment. Enrollment means you have to actually create a biometric profile or representation of your face, a model, and there you have to train the system. So there is an enrollment process for a user, for instance, which later should be able to authenticate to a system using his biometric facial features. The purpose of biometric face recognition in general is either identification, so we have a one-to-many relation. For instance, when you have camera surveillance in public spots, you usually try to find one or several bad persons on a list between many, many faces that are scanned. And another purpose, which I'm talking about, is authentication system, where you try to do a verification. So you want to see if a face that is presented to the biometric sensor, in this case an image of a face, is actually matching the trained enrolled profile of the user account you are trying to log into. So here we have a one-to-one relationship. And most biometric systems also have a thing called liveliness detection, because bio means live, and usually you want to only authenticate with living persons and not with dead ones or dead body parts. So that's also something that is implemented in most of the biometric authentication systems, no matter what biometric feature they are using. So fingerprint, for instance, the eyes, retina, the iris, or the whole face. Okay, so here are some simple definitions of the three important metrics I mentioned earlier. So the false reject rate actually is a measure of an authorized user being incorrectly rejected. The false accept rate is a measure of an unauthorized user, for instance, an attacker, being incorrectly accepted. And the equal or crossover error rate is just a measure of these two values being the same or nearly the same. So what you find in textbooks about biometric systems is this illustration here, which combines important terms, the FAR, FRR, the equal error rate, and also the so-called decision threshold that you have to define for your system. And depending on the purpose you're following with your biometric system, you have to tweak it in different ways. So for authentication purposes, you usually want the good person in and keep all the bad persons out. And you don't want to annoy the good person so that the system is actually usable. This means that the false accept rate should be usually low, because if this is high, somebody else can impose as another person and gain unauthorized access. You also want to keep the false reject rate low, otherwise you would annoy the user and he doesn't want to use this kind of system when he is rejected again and again and again and again. But you can't have both of these things, so you're trying to find a minimum for your specific purpose that you can live with. So the technology I have analyzed uses near-infrared, the Windows Hello Face authentication. Near-infrared is not a technical specific term, so it's actually a wide range of electromagnetic radiation, just besides the visible light band, the red light, with specific frequency and specific wavelengths, as you can see here. And the target of our research was Microsoft Windows Hello, as I've mentioned several times. That's the technology that is available since 2015, since Windows 10 was released. It's a core component of the Windows Biometric framework that also supports fingerprint authentication. And it's used for user authentication. Besides the fingerprint sign-in, you also have a face sign-in since 2015. And here's the definition or description of Windows Hello Face authentication by Microsoft itself. So Microsoft says Microsoft Face authentication is an enterprise-grade identity verification mechanism that's integrated into the Windows Biometric framework. And it utilizes a camera specially configured for near-infrared imaging to authenticate and unlock Windows devices, and also unlock Windows Microsoft Passport. And there are some key benefits using this kind of technology and using the infrared. And I have some slides later on that will describe the most important ones. Or the most important one is shown here below. It's the ability to provide a consistent imaging, even if you have different lighting conditions, like shown here. So one of the benefits using near infrared instead of visible light is you can have different lighting conditions in your room when you're authenticating to a Windows 10 device, and with an IR camera you can get a decent image where you can recognize the facial features quite well, independent of the visible lighting in the room, in the scene that the camera sensor actually can see. So that's why biometric face authentication systems usually use near-infrared currently. So, and here is how Microsoft measures and also defines accuracy concerning Windows Hello Face authentication. Well, there are false positives and true positives and false negatives. It's the same like the false accept rate and false reject rate. And you can also do the inverse logic here. So, I already described what's shown on this slide. So false positive is a value you want to be as low as possible, so that only the real person, the correct person that was initially enrolled to a specific user profile is able to authenticate to the system. And the true positive value is something you want to keep very high, otherwise you will annoy this person if it's, or if he or she is rejected again and again and again. Okay, And yeah, here's an interesting screenshot also from the Microsoft website that yeah, actually started a challenge to do some research on this topic, because near-infrared also has some benefits concerning so-called spoofing attacks, because due to the wavelength of this electromagnetic radiation and the available sensors, you cannot simply, for instance, put a photo in front of the sensor and see the image shown on the photo in the visible light spectrum. You cannot use an LCD display of different kinds, because yeah, the sensor sees actually only a gray area and no actual information where feature extraction can be done, as shown here on the slide from Microsoft on the side. So here's some general information I think most of you are familiar with. Authentication factors that can be used to authenticate to a system. There are actually 3 in general. It's something you know, so knowledge, like the good old password or passphrase, something you possess or have, so possession, like a token, smart card, USB, device of any kind, and inherence, something you are, so your biometric features, for instance, your face, your iris, your fingerprint, your palm print, stuff like that. And yeah, then you have single authentication factors and multi-authentication factors, and Windows Hello is a technology that only uses one of these factors, namely the face, the Windows Hello face authentication, which is not as secure as using several authentication factors. So there has been previous work of other researchers in the last decade. Here I've listed some of the work I am aware of and information I also used doing my research. So back in 2009, there was a presentation given by people from Deeg, if I know correctly, that also did the hack last year of the Apple Face ID authentication, and the title of this talk was "Your face is not your password." Yeah, unfortunately, some of the manufacturers still try to push biometric authentication during the last years, because it's a really convenient way for end users to authenticate to their devices. Then there's been a talk, Ich sehe, also bin ich du, by Starbuck a couple of years ago. There's been some research building virtual models from publicly available photographs to use this model to bypass face authentication systems 2 years ago. Then there was another talk and research done by Starbuck last year concerning hacking the S8 with the iris scan. And there was the famous twin-way hack against Apple Face ID at the end of last year by Deeg, the people who managed to perform an authentication bypass attack against the Apple ID face authentication system with the Apple iPhone X. So the background of the research we have performed actually was a customer project and some open questions we just couldn't answer back then at the end of 2017 or in September, October 2017. And we did some online research and looked, if there is some information about the security of Windows Hello, and information was rather scarce, so we couldn't find any resources that showed how it could be hacked or if it can be hacked and stuff like that. And the iPhone X, I already mentioned, with the Apple Face ID was to be released just within a couple of weeks in November 2017, so we thought, hey, it would be a good and an interesting target to have a look at Windows Hello face authentication, just to learn something about authentication systems in general and infrared technology. And our primary goal, of course, was to find an authentication bypass attack, because for us it's the most interesting attack vector. Okay, what we also found doing online research were several YouTube videos. Here are 2 examples where people tried to also do authentication bypass attacks against Windows face authentication back in 2015, shortly after Windows 10 was released. And they did experiments with twins, for instance, as you can see on the left, or they also did some test with photos, changing lighting conditions, masquerading, using makeup, and stuff like that. But none of these experiments actually were successful, so there was no information about a successful hack against Windows Hello face authentication. The test setup we've used was rather simple. We had, unfortunately, only 2 test devices. One was the Dell Latitude laptop. It's actually the laptop I have here, with a little bit USB infrared camera. And we also had a Microsoft Surface Pro device I've borrowed from our IT department. It's shown here. And we've tested different versions of Windows, so OS builds or revisions. The camera I've bought and I've used for testing was this one here. I bought it on Amazon because my Dell laptop doesn't have a Windows-compatible built-in infrared camera. So in order to use the authentication feature Windows 10 offers, well, I have to use an external USB camera like this one. And the description was also interesting. So the manufacturer says, or the vendor in this case says, it's recognized by Microsoft and also designed for Windows 10. And it has some kind of high-speed recognition login and masquerade detection and a depth sensor and high security biometrics. So some buzzwords that just got us more interested in this stuff. And also, masquerade by photos and images can be prevented. So stuff like that was in the Amazon description. So here's a close-up photo of this camera I've used. And, well, it actually consists of 2 cameras. There's a 720p RGB camera, and there's a near-infrared camera by Realtek. And what you can also see is near-IR LEDs for illumination purposes. So the camera does its own lighting or illumination of the scene. The sensor is taking an image of. And that's the second test device we've used. It's a Microsoft Surface Pro device. It supports Windows Hello with its built-in cameras. So it also has 2 front-facing cameras. One is a 180p RGB camera, and the second one is a specific Windows Hello near-IR camera. And here's a close-up photo of this device. Same setup, near-IR camera. Besides, there's an RGB camera. We have near-IR LEDs for illumination purposes or lighting, and there's also a status LED when the RGB camera is on. So then on this slide, you can see that when talking about a current Windows version, there is not only one current Windows version, but there are several current Windows 10 versions that are actually supported by Microsoft. And the software versions we've targeted at the end of last year mainly was the current branch per business, because that was the software version that was used by our customer. So it was 1607. But later on, we've also tested other software versions, 1703 and 1709. The other ones were just released after our research project. Okay, then what did we do? We had to set up our test setup, and the first and most important step is, of course, the enrollment process, so that everything works as supposed by Microsoft. What you can see here is a screenshot of the enrollment process performed on a Windows 10 version 1709 with the little bit USB IR camera. And what you can see here on this picture is the enrollment process of Windows Hello with the built-in IR camera of the Microsoft Surface Pro 4 device. And as you can see, one interesting thing is here you can see the actual IR image that the sensor sees. And when you enroll here using this setup, you will only see the image of the RGB camera and not the IR camera. So there are some differences concerning the hardware you use. And what's also important is the security feature that Microsoft provides concerning Windows face authentication. It's it's a so-called anti-spoofing feature or enhanced anti-spoofing feature. And I've only learned about this feature after reporting the first issues to Microsoft. because yeah, this security setting is not documented very well. So I didn't find it in the tutorials Microsoft provides in the description about Windows 10 face authentication when setting up our initial device setup. So it's a little bit hidden. But yeah, if you're using it in a production environment, you should definitely enable this feature. Our test methodology was plain black box test. So we made some assumptions about the inner workings of Windows Hello and about the capabilities a near-infrared sensor actually has and how we could possibly exploit the way of perception, so the way how these sensors perceive the world. Now, we did some simple development of yeah, very, very simple software tools we will see later on. The first one is just a software tool that allowed us to take images using the infrared cameras, so the little bit camera and also the built-in camera of the Surface device, so that we had access to the raw sensor data. And the second tool was a simple Python yeah, image processing tool. And then we did a lot of hard work and mind-bending research. No, just kidding, the rest was just trial and error. And within 3 days, we had the right configuration to actually bypass Windows Hello in our configuration we had. So when talking about biometric sensors, it's all a matter of perception. So here you can just see a sample screenshot of this very, very simple image capture tool we've used. And yeah, that's me in front of the camera. And this is the data the biometric system is processing. So the question was, how can we use this data for an authentication bypass attack using other display mediums, actually. So what we did, we tried different display options in order to show this required information to the camera sensor. So we tried different LED displays, for instance, an iPad 4, and what we found out is that the image that is shown on the display cannot be seen by the near IR camera. Then we tried out glossy photo paper, so the usual photos you can that were made back in the days. And here we also realized that the image that is shown on these photos can only badly be seen on the near IR camera. Then we tried out some paper printouts using inkjet technology because I had a very old printer at home. And I also realized, no, the image cannot be seen by the IR camera using a paper printout using inkjet technology. Then I also carried an old TV set from my basement up to the flat to test out if a cathode ray tube may work and if the sensor recognizes the wavelength yeah, actually provided by the cathode ray tube, but the image can also not be seen by the near-IR camera. Then I got hold of a fashion magazine of my wife, actually. It was a Cosmopolitan. And then I realized, offset print, a high-quality offset print on glossy paper, for instance, can be seen perfectly by the near-IR sensor of our test setup. And then I thought, that's a good direction to go. Unfortunately, I didn't have access, and I still don't have access to an offset printing machine where I can just print low quantities of photos to do some trial and error work. So I tested some other stuff, and that was, of course, the laser printer. And then I found out, yeah, the image can be seen well enough by the near-IR camera, not as good as having a professional offset print, but it was good enough for our purposes. So what you can see here is the really simple image processing. We did some trial and error with concerning brightness. I just Googled for this stuff and put it in a Python script. So this was just some code. I wanted to have full control over my test setup so that I can tweak with different parameters. And I had one for brightness and one for contrast, because at first I did some stuff with image magic and automation there, and then I did some stuff in GIMP, and I realized I don't actually understand what kind of algorithms they use, and if I tweak a slider or change a setting, what is actually done. So I just Googled for simple image processing algorithms where I could be sure that if I changed the value from 12 to 14, stuff changes like I really understand. So another thing to know was that the near cameras I have used actually had different image resolutions. So the cheap one bought on Amazon actually had a resolution 340 by 340 pixels, and the Microsoft Surface Pro camera had a higher resolution concerning the IR camera with 480 by 480 pixels. And we primarily used these two cameras for test purposes, but not solely. So we also used other IR cameras. For instance, we had a surveillance camera lying around that was also capable of doing near-infrared images, and this also worked, but it wasn't that convenient to use this kind of device, so we stick to both of these cameras to take our test pictures, modify the test pictures, and playing around with our test setup. And there was also an observation concerning the previously mentioned enhanced anti-spoofing feature. It is that when this feature is disabled, only the near IR camera is used by Windows Hello Face Authentication. And if this feature is enabled, both cameras are actually used for recognizing a face. What you can see here are original test images. On the left side, there is the raw image taken from the little bit camera. So it has a lower resolution, and what you can see on the right-hand side is 340 by 340 colored picture, and the color is important when dealing with the enhanced anti-spoofing, as we will see later. When considering only the size of the face and the actual data that is processed, the amount of pixels is even less. So for instance, in this picture, it's only 115 by roughly 190 pixels, and that is enough to actually identify me as a person, as we hopefully will see later on. So the attack surface and the attack scenario, I think, are rather obvious in this scenario. So the attack surface is a Windows log-on or lock screen. When Windows Hello is activated, so when you have a Windows Hello compatible camera, and face authentication was activated, and there are profiles enrolled that you can use to log in to the system. So the attack scenario actually is an attacker can gain physical access to a Windows 10 device with Windows lock screen or log on screen, and he tries to gain unauthorized access to your Windows operating system. So maybe he steals the device, or maybe he has just temporary access to your device, like the evil maid or cleaning stuff scenario. And the found security vulnerability actually was that it is possible to do an authentication bypass attack by spoofing. Otherwise, I wouldn't be here today. And it's actually possible to do it in a rather simple way. So all it takes is a paper printout for the attack with specific properties. And the properties are that the image has to show a frontal view of the person's face, because that is what the algorithm looks for. So he wants to see a face, he wants to see two open eyes, actually. So you cannot shut your eyes, otherwise you won't be recognized as a person or as a face. Then the image has to be taken with a near IR camera, because that's actually the data that is used for the feature extraction and for building the mathematical model in the background. And we found out that you have to tweak the brightness and the contrast of the images. And sometimes you also have to add some color to it, depending on the mode that is used for Windows 10 face authentication. In order to be successful with the attack. And the paper printout has to be of a specific kind. And as I've mentioned earlier, laser printer is okay. So the toner of laser printers has the right reflectance that it can be used for the near IR sensors to trick them. Okay, and now I will try to demonstrate this live. At first, against a virtual machine, I have set up somewhere here. Yeah. Okay, so here it is, generic IR. Okay, so now it's blinking actually, and as you can see, it could recognize me because I'm enrolled to this Windows 10 system, and it worked fine. So what I will do now, I will sign out again, and then I try to use one of the printouts I have here. I will show it to you in a second with the other camera and the other one, but let's see if the attack actually works. So here I have a grayscale printout that we've all seen in the slides before, and it's just a simple picture of my face. Yeah, and as you can see here, I get some hints. Make sure it's you, too far away, try moving a bit closer. So I'll try. Okay, now recognized. I just missed to slide it up. Okay, and I'm in. So as you can see, it works with a paper printout. And now I try to demonstrate just the same thing, but with our second test device, where the enhanced anti-spoofing feature is enabled. So let's shut this down. Then I will start up Cheese. Unfortunately, my other Python tool for the live cam doesn't work. I don't know why. This morning in the hotel, it worked just fine, but now I have to use this camera. Okay. Now, okay, it's booting up. So please excuse the bad image quality. So here's the same thing. It's a Surface 4 device. I'm enrolled to it, also using Windows Hello Face Authentication. Now I'll first check with my face if it can recognize me. So, and what I will use now is another processed image. I will show it here. So this one is colored. As you can see, there is a red colored layer, just an overlay to the other grayscale image. Because when enhanced anti-spoofing feature is enabled, both cameras are used, both front-facing cameras. So you need to have face information using near IR, and it also looks for some kind of colors using the RGB camera. And as you can see, it also works. For backup purposes, I also have a video here. I will also show it to you. We've published it actually a couple of months ago. No, where is full screen? It's just showing the same thing, but it's in one step, and also the enrollment process. Because here I have pre-configured the test setup, and in this video you can see that I'm actually performing the enrollment process before doing the attack. So this is one of our proof of concept videos. So here's the same test setup. It's the same Surface Pro device with Windows 10 16.07 and enabled enhanced anti-spoofing feature. And here I'm setting up Windows Hello Face Authentication for my test account with a real person's face, my own face in this case. Unfortunately, I only had my own face available when doing this video because I did it at home. And here you can see the screen we've seen before during the enrollment process. Then there's also the possibility to do improvement steps to the mathematical model. So I just did 2 enrollment steps here, or improvement. Then I'm testing if the device, the configured device, recognizes me. It's pretty fast. That's cool. It's really convenient. And here on the left side, you can see my attacker laptop. There is GIMP with a pre-processed image with the red-colored overlay. And now I'm simply printing this image on the laser printer the Surface Pro device is standing on. So here it is, my attack vector. And this image was taken by the low-resolution camera with 340 by 140 pixels, and as you can see, yeah, it worked. So it was a newly trained system and a paper printout. Yeah, and just to make it true. Yeah. Okay, so here are our actual test results concerning different Windows 10 versions we've tested. So it was back in 2017, end of 2017. And what we found out is all versions we have tested with the little bit camera, with our test device number 1, where actually we were able to successfully attack the authentication system. And it was mainly because of the enhanced anti-spoofing feature was not available using this kind of camera because it is not supported. But we couldn't find any information about this case. We just learned later on that not all cameras that are Windows Hello compatible are fully Windows 10 or Windows Hello compatible. And concerning our second test device, the Microsoft Surface Pro 4, we managed to perform authentication bypass against older versions of Windows, or not older, but the current branch for business. It's 1607 back then, and it still is the current branch for business, with and without enhanced anti-spoofing. And when turning on enhanced anti-spoofing, we were not able to use the method I've shown here for targeting Windows versions 1703 and 1709. So this security setting, enhanced anti-spoofing, actually really makes a difference. So the conclusion is that Windows Hello face authentication can be bypassed by rather simple means. So I've used a paper printout with a photograph taken by, it depends, a special camera, it's near IR. And you can perform this attack against different Windows 10 versions, but not all. So it depends if you're successful with this attack regarding the hardware that is used and the software configuration. And what we've also learned is that the enhanced anti-spoofing feature is actually not supported by all near-infrared cameras that support or can be used for using Windows 10 face authentication system in the default configuration. So our recommendations actually are to use newer Windows 10 versions because Microsoft is aware of these kind of attacks and they have tweaked their system consistently. Unfortunately, we were not able to find any publicly available documentation about Windows 10 and the parameters. So they seem to change the algorithm behind the face authentication system, but they just don't document it publicly. And yeah, of course, you should only use Windows Hello compatible cameras that support the enhanced anti-spoofing feature. And you should actually enhance this feature. And if you enhance this feature after you did an enrollment process, you should re-enroll. Otherwise, you will still be vulnerable to this attack. So that was also one of the things we found out. So we used an older version, 1609 or 1607, I think, did the enrollment and later updated Windows. And then we found out, hey, we can still perform this attack. But when we did another re-enrollment, the attack wasn't possible anymore with the enhanced anti-spoofing feature enabled. So reconfiguring Windows Hello is very important after a Windows 10 setup. Yeah, and I also have ideas for further research. Unfortunately, I didn't have the time, well, the last couple of months. But what I want to try out is using actually not one, but two paper printouts, because when the enhanced anti-spoofing feature is enabled, well, you have two cameras, a near-IR camera and an RGB camera, and information from both sensors is used to make the decision if you are the real person or the correct person for the profile you want to log in or not. So one simple setup would be to have two angled mirrors 90-degree angle, and then just present the near IR camera a near IR photo, and the RGB camera a complete RGB photo. I started this kind of attack with a very simple setup and didn't succeed so far, but maybe it works with a more sophisticated setup. Who knows? But that's my idea for further research. And yeah, here are some references. So thank you very much. That's it.
My question is, have you tried to plug in a camera while the user is logged out, so that you can use a camera without this anti-spoofing protection? So even if the device have this protection and you plug in a camera that doesn't support, then can you still log in?
Yes, I've also tried this kind of attack. So attaching a second camera, for instance, to the Surface Pro, where there is already a built-in one, the built-in camera is used. Was that your question? So
yes.
Attaching a second device with less capabilities concerning security, yeah, unfortunately, this didn't work.
Okay, thanks.
At least concerning USB devices. I don't know what would be if I would open up the Surface Pro and destroy or remove the built-in camera and then give the device an external USB camera. I haven't tried this because it's only a borrowed device. I have to give it back working.
Yeah, my question is if you have reverse engineered the DLLs that are responsible of the enhances and the spoofing and stuff to know actually what are they doing.
I started, but it is a lot of work. Yeah. So that's why the black box approach. That is what we followed, and we were successful within 3.5 days, I think. But I think it's still interesting, and also I think for further research, actually reverse engineering how the biometric face model is built, how the data is stored, and if you can find other attack vectors for spoofing attacks, for instance. Yeah. Oh, I think so. Yeah, but it's a mixture of technologies. I think most stuff is C++, and then there is some stuff in .NET, and there's also logging capabilities. So you can turn on logging, where you can see what was I think the confidence level of the last login or why it failed. Yeah, for further purposes, but. It's also something I learned actually afterwards after I talked to Microsoft, and they said, you can also do this and that, and can you provide us with this information from the log files I wasn't aware of when starting the research, actually. Okay, so thank you very much.
Okay, then again, thank you very much, Matthias.